Right then, as I've been promising for the past couple of weeks, we're finally going to get on to the idea of covariance. And this is a concept that's related to inheritance. It's actually something related to the Liskov substitution principle, the rules for inheritance that we looked at earlier on. And it addresses an age-old question in object-oriented programming, something that I remember discussing back in the early 90s when I first started programming in C++. And that is the strange question: is a bag of apples a kind of bag of fruit? That's to say, if you've got two classes, a bag of fruit and a bag of apples, is it valid to have an inheritance relationship between them? So let's take a look at that idea. And here I've got it diagrammatically. And so what we've got here is a base class fruit, and I've derived from that a couple of fruit, apple and banana. So an apple is a kind of fruit and a banana is a kind of fruit. And we'll just take that as read. That's fairly straightforward inheritance. But then when the issue comes is when we have collections of these things. So I'm just saying I've got a bag of fruit that contains specifically fruit. If this were done in C#, it would be a generic instantiated for fruit. And then we've got a bag of apples, and that, as we can see, is a collection specifically of apples. And so the question we're asking is, given that we've got the inheritance relationship between fruit and apple like that, is it correct for us to have an inheritance relationship where bag of apples is derived from bag of fruit? And ostensibly, it might look okay. But remember the tests that we were looking at when we were dealing with the Liskov substitution principle. We said when we have two classes, we want to say something like a manager is a kind of employee who additionally has certain features like a budget. But what we must avoid saying is a manager is a kind of employee, except that they don't, and then maybe have something like overtime or whatever it might be. So let's consider bag of apples and bag of fruit. Certainly, we can say that there are lots of features a bag of fruit has that a bag of apples also has. So a bag of fruit has a number of items. A bag of apples will have a number of items. A bag of fruit is something that can be delivered, say. A bag of apples can be delivered. We can also say a bag of apples has additional features. You can make an apple pie out of a bag of apples. You can't do that to a bag of fruit. But the one we've got to ask ourselves, as we talked about with the LSP, is there anything you can do to a bag of fruit that you can't do to a bag of apples? And the answer is yes, because you can put a banana into a bag of fruit. Let's just think about that. So a bag of fruit can contain any fruit you like, apples, bananas, pears, whatever. So one of the things you can do to a bag of fruit is put a banana into it. Clearly that's not something that you can do with a bag of apples. A bag of apples, you can only put apples into it. Therefore, we've attempted to remove functionality. Therefore, we don't have inheritance. So simple answer is no, we don't have inheritance there. A bag of apples is not a kind of bag of fruit. But it only went wrong on one particular method, the add method, when we're trying to add fruits generally or add apples specifically. If we could have a bag of fruit that didn't have an add method or anything like that, then maybe we'd be okay. But then, of course, you've got to ask yourself, well, what's the point of having a bag of fruit or any container that you can't put things into? And that's a perfectly valid objection. But let's also think we don't always have to talk about classes when we're dealing with OO. We can talk about interfaces. And if we think along the lines of the interface segregation principle, we can take something like a bag of fruit and break it down into smaller interfaces along the lines of different aspects of its behavior. So we could have one interface that deals with things like adding and removing items, and another interface that deals with the commonality of being able to count them and that sort of thing. And if we can break it down like that, then we can find that if we're dealing with interfaces here, so if this is not a bag of fruit, but the most common interface we have, an Ienumerable of fruit, and it's not a bag of apples, but an Ienumerable of apples, because Ienumerable has no methods that allow you to assign into it or add into it, then we have no methods that break the Liskov substitution principle. And so if these are Ienumerables, then we can have inheritance between them. So let's take a look at that in terms of some actual C#, because C# supports this idea that when we're dealing with things like interfaces, we can have this assignment, and this is what is known as covariance. So what I've got here is, firstly, I've got an example of doing this wrong. So what I've done is created a base class called bag of fruit. that we can see there. And so it actually stores the fruit as a list in this case. And then it's got a get method, which should be okay, that just reads the fruit. And then it's got an add method. And this is what we know could be the problem, where we add fruit. Then we've also, derived from that, got our bag of apples. So we can see there, bag of apples derived from bag of fruit. And we've done a bit of cheating here. We've done a get, which is now actually having to hide the original get because it's a different return type. This is returning apple, whereas previously we were returning fruit, and it takes the value and casts it. But then also, and this is where the problem's going to arise, the fact we've got the add, that we can add an apple to a bag of apples, whereas we can add fruit to a bag of fruit. And then we've also just got examples of our fruit. So there we've got the base class fruit, there we've got the apple, and there we've got the banana. And so if we take a look at what's happening here, in our main program, I'll start out with this one that we're calling breaking LSP. So this is using my classes that deliberately break this idea. There we've got our bag of apples. We add a new apple into it. We print out that apple. And that works fine. But then we can see the problem that because a bag of apples is a kind of bag of fruit, so remember we put that inheritance relationship in there, that means that we can add a banana to it, because a banana is a kind of fruit, even though a banana is not an apple. And so again, up to that point, actually, that will work, but we've already hit the problem, because now, as soon as I try to get that item, then we'll get an error. It's actually an invalid cast, because our bag of apples actually is now trying to cast that, and that's not allowed. That's where it's all going wrong. So that was an attempt to actually get this wrong, to have inheritance where it doesn't apply. It required a typecast to make it work, and that was the thing that ultimately caused the failure. But the real problem was one of getting our inheritance wrong. So let's not do that. Let's move on and look at the second part of this, which is to actually do it the right way using the built-in features we've got with generics and Ienumerable. So now, not writing my own class, I've just got this list of apples. So list instantiated for apples, and then I say I've got this Ienumerable of fruit. And then here's the thing that we are now allowed to do. We can take the variable bag of fruit and assign into it the bag of apples. And that's what's showing we have a valid inheritance relationship between Ienumerable of fruit, the base class collection, and in this case, list of apples, the derived class. So the fact that we've got the inheritance relationship is why that works okay. And so now we could just iterate through our collection of fruit, and obviously we can't treat them specifically as apples, we can only treat them as fruit, but that's fine, fruit has a name. If we then add a new apple to our bag of apples, we can't add an apple to our bag of fruit, but we can add it to our bag of apples, then print them out again, and we'll get even more of them. So if I just run that, then you can see we get the original collection of apples, then we added a new apple to it, but we can still print it out. So the key thing is, this bag of fruit is just a reference to the bag of apples. It's not a copy, it is a reference to the same item using this idea. What we can't do though, is we can't add a banana. Obviously, we can't add a banana to a bag of apples, because although bag of apples has an add method, because it's generic for apple, we can't add a banana to it. But similarly, we can't add a banana to a bag of fruit. Not because a bag of fruit can't contain a banana, because a banana is a kind of fruit, but because we don't have an add method on an Ienumerable, deliberately, so that this whole thing will work. So in neither case can we add a banana, either through the actual list or through the interface. How does that actually work? It actually works, if we look at the Ienumerable interface, it works because in the generic declaration, we've got this keyword out. And this says that the data type T that we instantiate the generic for is a covariant type. And that's what allows this to work. It tells us that we're allowed to derive from Ienumerable of T an Ienumerable of anything that is itself derived from t. Might be a bit clearer actually if we put that together for ourselves. So this next example I've got is to do this thing with a homemade class and interface. So I've actually introduced here, in a cut down way, the same sort of thing. So here I've got my interface that I've just called iBag, and I've made that a generic with the keyword out on it. So you're only allowed to do this on generic interfaces, actually, not on generic classes. It's only to do the interfaces, but we've declared that as a covariant parameter by putting the word out on there. And then having done that, we've only given it a get method. We haven't given it an add method, because remember, add method was the problem. And then we've got a class which implements that interface. And again, this bag is a generic class. Again, I've just used a list to actually store the data. It has to implement the get method from the interface. And then additionally, nothing to do with the interface, I've put an add method on there so we can put whatever this type t is in there. And then if we look at our program for this one, down here, we can see there we create our bag of apples, there we populate it. And again, exactly the same thing. We can have an interface for a bag of fruit and put into it a bag of apples. And that's exactly what we're doing there, only with my own types rather than with the standard ones. And I'm not sure I do this very often, but it's just showing the idea that we can do this for ourselves. Much better, if possible, just use one of the standard classes. And so having done that, I can do the same sort of thing. So I can put that in there and then just read through my iBag of fruit interface each one of the apples. So that's what we've got with that use of the keyword out. And let's just show what would happen if we didn't have that. If I remove that out, we're still allowed to implement the interface. But if we actually look in the program, we're no longer allowed to have our bag of apples assignable into our interface for iBag of fruit, because we no longer have the inheritance relationship. So without that out, we don't have the inheritance relationship between those two collection classes. So that's not allowed. So we put that in there, but having it in there means that certain other things aren't allowed. What I can't do, because I've got the out, is I couldn't do something like this. I couldn't say void add and then something like maybe t_obj. So I'm not allowed to declare my add method in the interface because that says out. If it doesn't say out, then I am allowed to, but I lose the inheritance over here. But if I put the out on there, then that becomes an error, because that would then break the LSP for the reasons we saw. And that kind of tells us why the keyword out is there, because what it's telling us is we can only use t for return types from methods and properties, essentially. We can't use it as parameters that are being passed in. So it can only be coming out, it can't be going in. So that out keyword gives us a benefit. We've got the inheritance between the collections, but it restricts us. We can only use this interface for reading the data, not for writing the data. And so back in our main, that means that we can't add bananas either to the bag of apples or to the bag of fruit for exactly the same reasons we saw earlier with the Ienumerable, because in one case a banana isn't a kind of apple, in the other case the bag of fruit doesn't have an add. So really quite straightforward. In terms of actual C# programming, it's just a case of adding that out keyword to the generic parameter. Even though in terms of the logic behind it, there's quite a lot of theory, usage of it is very simple, and made even simpler because we don't very often have to write this for ourselves. It's there in Ienumerable and other interfaces where it makes sense. There is one slight caveat to add here though. This is also available in arrays. So if we just go back and look at one last example, what I've got is I've declared simply an array of apples. So not a list or anything like that, just a simple array. But then I've declared an array of fruit. And assigned into that an array of apples. So that is telling us that we do have this inheritance relationship, that an array of apples is a kind of array of fruit, just like an Ienumerable of apples is a kind of Ienumerable of fruit. And obviously that means we could either loop through the array of fruit, or we could loop through the array of apples. We'll get exactly the same results for each of those. But then comes the oddity. If we've got our array of fruit, although you can't add to an array because an array is fixed size, you can do something with an array that you can't do with an Ienumerable. You can assign into it. And so perfectly okay to say array of fruit item 1 equals a new banana. So we're not adding, we're simply overwriting the original apple with a banana. And that's just as bad. Okay, it's not adding, but it's still putting into an array of fruit something that is, in this case, not an apple. And we'll see that immediately now, that we get the same sort of error. Attempt to access an element of the wrong type. Exactly the same as I had when I tried to fix this for myself, when here we added a banana to a bag of apples. Well, here we're assigning a banana into an array of fruit. And that's actually, I would say, a fault in the C# language. Although there are some conveniences to this, logically speaking, it is a breach of the LSP to say that we can assign an array of apples into an array of fruit. We do not have correct covariance here because you can still assign into an array. Thankfully, of course, we try to avoid using arrays for various reasons. Sometimes they're useful. Occasionally this will hit you as a problem and you'll learn not to use it. But when we're dealing with interfaces and lists and Ienumerable and that sort of thing, then everything is nice and safe, and it's that out keyword giving us a covariant generic type that makes it all work. You may be thinking, if we've got an out keyword, do we also have an in keyword? And you're absolutely right. We can put in rather than out into generic, and you can see immediately we're getting an error there. And that, you may easily be able to guess, is what is known as contravariance, and that's going to be the subject of the next video. So I hope all that made sense. Any questions, put them in the comments section below, and also do please subscribe, and see you next time.